All right, hello and welcome back. So in the previous video, we derived the Lagrange equation, at least the basic principle that we call Lagrange's principle. Now let's refine that principle for a couple of conditions in this video and the next one. The first video is studying the condition that the system only has holonomic constraints and essentially is unconstrained. And by that, actually now that I've written it, it is a little confusing. So let me write it down. Consider a system with holonomic constraints. And this unconstrained one, what I mean is, and all is that, what kind of all is that? All Q's are independent. So that wouldn't be possible. For instance, well, no, even then that's possible. So you may have a closed kinematic chain like a four-bar mechanism, and you're considering all angles as your generalized coordinates. So in that case, all the Q's are not independent. And this is not the condition we're considering. We are only considering situation when we have, if our system is n degree of freedom, we have n Q's. So that is the condition we're considering. So if you remember, the equation we had last time was sum I from 1 to n of d over dt partial t partial q dot I minus partial t partial qi plus qi delta qi equals 0. So that was what we called Lagrange's principle. So now going to this condition, all Q's are independent. That means I can take all these delta Q's, virtual displacement, to be arbitrary, or I can change them arbitrarily, and still the summation has to be equal to 0. In this case, what it means is this factor, or the whatever is in the parentheses, has to be 0. So in this case, d over dt of partial t partial q dot minus partial t partial qi for all I equals 1 to n. So that is a very nice form. So if your system only has holonomic constraints and Q's are independent, we can do this. So we have, maybe I can explain this here. We have this statement, constraint has to be holonomic, because if the constraints are, well, actually, if the constraints are not holonomic, or there is at least one non-holonomic constraint, then you have to have more Q's than degrees of freedom, and some of them involve constraints. So that is why we are saying the system is holonomic. So that is nice. Let's consider two subcases. One is if all forces are conservative. So all forces acting on the system, all external forces are conservative. In this case, we know these QIs are some partial derivatives of a potential function v, and v is only a function of positions and possibly time. So we know our generalized forces can be written in such a way. And let's do that. Let me bring this to the other side. So I have d over dt of partial t partial q dot I. I'm going to leave some space here for future. Minus partial t partial qi minus partial v partial qi equals 0. So all I've done is bring this partial derivative to the other side. So this is equal to partial t minus v partial qi. And remember, v is only function of q. So partial v partial q dot. Let me write this slightly better. Partial v partial q dot is actually 0. So what I can do is change this to t minus v2, because partial v partial q dot doesn't change anything, that's 0. And now I have two terms, t minus v. And that is what we have. So let's define this L, which is a function of q, q dot, and t, to be t minus v. Let me try it this way. T, which is a function of q, q dot, and possibly time, minus v, which is function of q and time. And this is what we called Lagrangian function. It is very useful and important. So Lagrangian is T, the kinetic energy, minus V, the potential energy. This may look a little weird because we usually add these two together to get the energy, but through this math, you can see why the negative is effective. And from here, I can write d over dt of partial L partial q dot minus, partial L partial qi equals qi. And this is what we call Lagrange's equation, or this is the holonomic form, the holonomic form. So to use it, I can find the potential energy and kinetic energy of system with respect to, or as a function of my generalized coordinates, and then write this equation. This is practically the equations of motion for the system. So this exactly gives you the equation of motion. And we'll see later in examples how we can use this very easily to construct equation of motion for a system. And the other case I can consider is if there are non-conservative forces. So in that case, what I can do is write my qi, separate essentially the conservative and non-conservative forces. So my total force is the summation of the two. So the conservative part is going to be same as before. And I'll have some, not the star. some Q, what do I have? Q prime. Some other generalized forces only because of the non-conservative forces. And using exactly the same procedure, bring this to the other side, define Lagrangian and everything. What I have is d over dt of partial Lagrangian, partial q dot I minus Lagrangian qi. Wait a minute, why did I have qi here? This equals 0. My apologies. Now this equals q prime I. So this is the second form comes very handy if you have external forces on your system, external forces and torques on the system, and while all the while your system is being acted also by some potential force, some gravitational forces and spring forces and all other conservative forces. So this is how we can use to include those external arbitrary forces in the equations. So okay, and here I have to iterate or be that we can write this for any of those i's. So for any of the generalized coordinates for both of them. Anything else I need to add? No, that's it. We'll see some examples how useful and easy it is to use these Lagrangian and Lagrange equations to formulate the equations of motion for the system. But for now, that's all we have, and I'll see you soon in the next video.